Imagine electric potential as a physical hill. If you drop a ball at the top, it naturally rolls downhill along the steepest, most direct path. In electrostatics, the electric field acts exactly like gravity on that hill, pulling charges straight down the gradient. The steepness of that slope dictates the exact strength of the field. A steep drop means a strong field. Since the field always pushes from high potential to low potential, we use a negative sign to indicate it points down the slope. We can translate this physical hill directly into math. This boxed differential equation shows exactly that relationship. A tiny change in potential, dV, equals the electric field dotted with a tiny step in distance, dr, with the negative sign ensuring we're moving downhill. To find the total drop in potential across a large distance, we integrate both sides. By adding up all those tiny steps, we calculate the total work done by the field as a charge moves from an initial point to a final destination. Taking a derivative to find the field, or taking an integral to find the potential difference, are just two ways of reading the same topographical map. Let's apply this to a 1D radial potential function. This problem gives us the potential, V equals K over R, and asks for the field. We set up our derivative, finding that the slope of 1 over R is negative 1 over R squared. But remember, potential is a scalar value, and electric field is a vector. The derivative alone just gives us the magnitude. To fully define the field, we have to append the direction manually by adding the r hat unit vector. Real space is rarely one-dimensional. Here, we have a three-dimensional Cartesian equation for potential. To find the field, we have to evaluate the steepness of the slope along three separate axes. We start by taking the partial derivative with respect to x. The rule here is strict. When you evaluate one axis, every other variable is treated as a flat constant. Because we are only looking at changes along the x-axis, the partial derivatives for the y and z terms completely zero out. The x component of the field is simply 5. Repeating that process gives us the y and z components. To find the true magnitude of the field, we recombine these isolated 1D vectors using the 3D Pythagorean theorem, yielding a final field strength of 7 newtons per coulomb. In multidimensional space, the true electric field is the vector combination of the individual slopes measured along the x, y, and z axes. Now let's reverse the flow. This problem gives us a constant 2D electric field vector, 20 in the x direction and 30 in the y direction, and asks us to calculate the potential at a specific coordinate. Pause here for a second. Knowing the field is constant, look at how the problem sets up the integral. We align our x boundaries from 0 to 2 and our y boundaries from 0 to 2, effectively calculating the area under a flat line. That works perfectly for constant fields, but non-uniform ones require a different approach. Look at this intimidating line integral on the left. We're asked to integrate the field from a non-conducting ring from infinity all the way to its center point. Brute forcing that calculus is a nightmare, but there is a shortcut. By definition, the negative line integral of an electric field perfectly equals the potential difference between those 2 points. We can drop the integral entirely. We just use the standard scalar formula for the potential of a ring at its center, subtract the potential at infinity, which is 0, and solve the problem with basic algebra in a single, simple step. Recognizing that this specific integral is a mathematical representation of potential difference allows us to bypass the complex calculus entirely. We can apply all of these rules visually without a single formula. Look at this graph showing diagonal equipotential lines at 40, 30, and 20 volts. We need to find the field's properties strictly from this geometry. First, the direction. Because the field pulls straight down the steepest slope, it always locks into a perpendicular right angle with the equipotential lines, pointing toward the lowest voltage. To calculate the steepness, we need the distance. But we can't use the horizontal 1 meter gap along the x-axis. The true gradient requires the shortest, direct, perpendicular gap between the lines. Using the provided 45-degree angle, we pull out a tiny geometric triangle to calculate the true distance as 1 over root 2. We plug that true distance into our basic gradient equation, change in voltage over change in distance. A 10-volt drop divided by our geometric gap gives a final electric field magnitude of 10 root 2 volts per meter.
Every method we've covered maps back to the same relationship. To go from potential to field, use partial derivatives. To go from field to potential, use integrals. And on a graph, just look for the steepest perpendicular drop. Whether you are manipulating pure algebra, crunching 3D calculus, or mapping out graphical geometry, the electric field is consistently the spatial rate of change of the electric potential.